Hi everyone, in this video I'm going to explain the concepts of self and mutual inductance concepts along with the dot convention principle. First of all, the property of an inductor is called as inductance. This is also called as self-inductance. The flux produced in a coil due to the current flow in the same coil is called as self-inductance. That means if in a coil a current is flowing, so then the flux is produced in the same coil, so this phenomenon is called as self-inductance. So we can also define self-inductance as the property of the coil which opposes the change in current passing through it is called as self-inductance. So it is designated with a letter L and it is measured in the units henries. So from the Faraday's laws of electromagnetic induction principle, we have written V is equal to N into d phi by dt. From the second law of Faraday, we can write V is equal to N into d phi by dt. So where d phi by dt can be rewritten as by multiplying, dividing with the current, so phi by I into di by dt. So and resubmitting in this equation V is equal to N into d phi by dt. So here we have a term N phi by I. So this N phi by I is called as a constant L. So therefore L is equal to N into phi by I. So this L is called as a self-inductance, where V is equal to L di by dt. This is the voltage across the inductor formula. So physically inductance can be measured as, so we have already from the Faraday's law's formula, N into d phi by dt is equal to L into di by dt. So equating these two formulas, V is equal to N d phi by dt and V is equal to L di by dt. So equating these two and simplifying these, N d phi is equal to L di. So and if you write N phi is equal to L into I, and from the flux density formula B is equal to phi by A, it implies phi is equal to BA. By substituting this phi formula in this equation, NBA is equal to Li. From this L is equal to NBA by I. So already we know that B is equal to mu H formula. By substituting here B is equal to mu H, so we are getting N square mu H A by N into I. Just we are dividing and multiply with N here, so that we are getting, so N into I nothing but called as MMF. We have other formula, MMF is H into L. Therefore by substituting H into L, here H gets cancelled. Therefore L is equal to mu N square A by L. So this is the other formula for inductance if the physical parameters are known for us. That is N is the number of turns, A is the area of cross section of the coil, L is the length of coil, and mu is the permeability of the medium. So where mu is nothing but permeability of the medium given as mu naught into mu r. Mu naught value is 4 pi to the power of minus 7 Henry per meter. Mu r value is relative permeability, its value is 1 for air or vacuum. So N is the number of turns, A is nothing but area cross section of the conductor measured in meter square, L is the length of conductor measured in meters. So next, if we see the concept of a mutual inductance, when two coils are electrically isolated and mounted on an iron former, that is core, so the flux linkages in one coil is due to the current changing in the other coil. That means if the current is changing in one coil, flux is produced in the another coil. So this concept is called as mutual inductance. So let N1, N2 are the number of turns and I1, I2 are the currents in the coils 1 and 2 respectively, and phi 1, phi 2 are the total fluxes linking in the coils 1 and 2. So due to the currents in the I1 and I2. So also let phi 1 1 and phi 2 2 are the fluxes linking with the coils 1 and 2 due to the currents I1 and I2, and phi 1 2 is the flux linking the coil 2 due to the current in the coil 1. So here 1 2 stands for, the 1 stands for current in the coil 1 and 2 is nothing but the flux in the coil 2, and similarly phi 2 1, here 2 stands for the current in the coil 2, 1 stands for flux in the coil 1. So in this way we are defining the terms phi 1 1, phi 1 2, phi 2 1, phi 2 2, like these definitions. And also along with L1 is the self-inductance of the coil 1, L2 is the self-inductance of coil 2, M12 and M21 nothing but mutual inductance of the coil. So next, the self-inductance of coil 1 is given by the formula L1 is equal to N1 phi 1 by I1. Similarly, self-inductance of coil 2 is given as L2 is equal to N2 phi 2 by I2, and the mutual inductance between the coils 1 and 2 is 1 M12, that is M12 stands for 1 stands for current in the coil 1, 2 is nothing but flux in the coil 2, therefore N2 512 by I1, here I1 is the current in the coil 1, therefore flux in the coil 2 is 512, and the mutual inductance between the coils 2 and 1 is M21 is equal to N1 521 by I2, where 512 and 521 nothing but proportional to the fluxes by a constant K, therefore 512 is equal to K51, 521 is equal to K52. Therefore, by replacing these two terms in the two equations M12 and M21, we are getting, and multiplying those two equations M12 into M21. So, and by substituting these values 512 and 521 with K51, K52, and we are getting K square into N151 by I1, N252 by I2. So these two terms we can call as L1, L2. Therefore, M12 into M21 is equal to K square into L1, L2. It's because symmetrical arrangement, we have same inductance between the two coils there. Therefore, M12 is equal to M21 is equal to M. Therefore, M square is equal to K square into L1, L2. It implies M is equal to K root L1, L2, where K is called as coefficient of coupling, that is given as M by root L1, L2. So, if the coils are placed closely on iron core, then K is equal to 1. If the coils are placed apart in the air, then K is less than 1. In the transformer with iron core, K is approximately equal to 1. So next, dot convention principle. So the mutually induced voltage is positive. The current should enters or leaves at the dots in the all the coils. That means if the two coils are connected parallel or series, and if the dots are placed either at the sending end side or receiving end side of the coil, so then the mutually induced voltage between the two coils is positive if the current is should enters or leaves at the dots in all the coils. Similarly, the mutually induced voltage is negative if the current is entering at a dot for one coil and the current leaves at the dot in the other coil, or vice versa. That means if two coils are connected, then the current is entering at one dot for a coil, and for other coil the current the dot is placed at the dot is there at the current leaving side, then such case is said to be that means the mutually induced voltage in such case is negative. So equivalent inductance of the coil with mutual inductance. So in the absence of mutual inductance, the equivalent inductance between the coils when connected series is L equivalent is equal to L1 plus L2. So if the two coils are connected in series by with the dots and there is exists a mutual inductance, then by dot convention method we can write the equivalent inductance value as L1 plus L2 plus or minus 2M, where plus or minus is nothing but where plus stands for series aiding, minus stands for series opposing. So here the pictures shown the cases for series aiding and series opposing. So the figure A, if you observe the figure A, so the dot is placed at this point, and for coil 2 the dot is placed at this point. For example, if the current is entering in this side, so the current is entering in this side. For this coil, the dot is placed at the current entering point. For this coil also, current dot is there at the current entering point. Therefore, such case is said to be series aiding. So in the figure B also, the dots are there at the current leaving from the coil. Therefore, this case is also said to be series aiding. So similarly, for the figure C, in the figure C, for coil 1, the dot is placed at the current leaving side, and for coil 2, the dot is placed at the current entering side. So this is called as series opposing. So in the case D also, for coil 1, the dot is placed at the current entering side, and for coil 2, the dot is placed at the current leaving side. So this case is also called as series opposing. So for series aiding case, the formula is L1 plus L2 plus 2M. For series opposing case, the formula is L1 plus L2 minus 2M. So similarly, the two coils are connected in parallel without any mutual coupling, then the equivalent inductance is given as L equivalent is equal to L1 L2 by L1 plus L2. Suppose with the help of mutual inductance is there, then the formula can be given as L equivalent is equal to L1 L2 minus m square by L1 plus L2 plus 2m, where plus is for parallel opposing, minus is for parallel aiding, and the corresponding figures are shown here. So here the two coils are connected in parallel and the current is entering in these cases. In the case A, so if you see this figure, for the two coils current is entering at the dot point, therefore this case is called as parallel aiding. And in the figure B, the dots are placed at the current leaving position, therefore this case is also called as parallel aiding. So the case C, for coil 1 the dot is placed at the current entering point, for coil 2 the dot is placed at the current leaving point, therefore this case is called as parallel opposing. So here also for coil 1 the dot is placed at the current leaving point, and for coil 2 the dot is placed at the current entering point, so this case is also called as parallel opposing. So for parallel aiding we have the formula L equivalent is equal to L1 L2 minus m square by L1 plus L2 minus 2m, whereas for parallel opposing L1 L2 minus m square by L1 plus L2 plus 2m. So here the plus stands for parallel opposing, minus stands for parallel aiding. So we'll see a problem based on this concept. So two identical coils with L is equal to 0.03 Henry having a coupling coefficient 0.8. Find the equivalent inductance with two coils connected in series aiding and opposing, parallel aiding and opposing. So we have the formulas in the previous section. We have know the formulas. Given the data, L1, L2 values as given 0.03 Henry, K value is 0.8. Therefore, M is equal to K into root L1, L2. The M value is not given, so we have to calculate the M value, and the coupling value is given as 0.8. By substituting these values here, we are getting M value as 0.024 Henry. After getting this M value, we have to calculate the equivalent inductance in the four cases. First case, series aiding. If the case is series aiding, the formula is L1 plus L2 plus 2m. By putting all the values L1, L2, m here, we are getting L equivalent as 0.108 Henry. In case of series opposing, so here the formula L1 plus L2 minus 2m, therefore the inductance value here getting 0.012 Henry. And similarly, in case of parallel aiding, we are getting L1 L2 minus m square by L1 plus L2 minus 2m. So here the inductance value is 0.027 Henry. And finally, in case of parallel opposing, L1 L2 minus m square by L1 plus L2 plus 2m, here the equivalent inductance can be given as 3 millihenry. So this is a way to calculate the problems based on this concept. Thank you.